So here's where we are, just for reference. I forgot altogether that today is St. Patrick's Day. I see that some of you are properly wearing green, but I managed to forget. So anyway, today we're actually going to be talking about synchronous reactive models. This is kind of a vacuous lecture that I will largely bundle into this because I think we've already talked about the contents of that already. Right after spring break on that Tuesday, I remind you that your project milestone reports are due. This is a one-page milestone document explaining where you are. And then 1 week later, the following Tuesday, we will once again do 5-minute project presentations. Okay? So the project starts to get kind of relentless at this point, and we're trying to make sure you don't let it slide, because if you let it slide, it gets really hard at the end of the semester. So, and I strongly encourage you to actively seek out your mentor and actively seek out me or Sanjit if you have any questions or concerns about how your project is going, okay? Any questions that you guys have for me at this point? Okay. Well, let's start into today's topic. And today's topic is going to be about better ways to do concurrency. So what we've seen so far is kind of a two-layered approach, where at the lowest layer, closest to the hardware, concurrency arises because you're doing I/O and you're having interrupts occurring, which are executing pieces of code at arbitrary points, having suspended some code that executes in your microprocessor. It can also arise if you're operating on a multi-core machine, okay, or on multiple CPUs. That also will lead to a concurrency scenario where you have to worry about shared resources at the hardware level. One level up from that, at the operating system level, you've got threading, multi-threading that's going on, where your interrupts are timer-driven typically, and a scheduler makes a decision about which threads to resume at any given time. And we spent the last couple of lectures trying to get our heads around the scheduling problem in the context of real-time constraints. And so today, what we're going to do is we're going to pop up one level further and say, well, if you do concurrency at the level of threads, I think we've seen that things can get very confusing very quickly and very difficult to understand. And so the question is, how can you mitigate that? I mean, the fact is that today's architectures force you to do some form of threading if you're going to have concurrency going on at all. Okay, if you have a single CPU, then timing constraints or I/O require you to do interrupts, where an interrupt service routine is a thread in the sense that it's a sequential process that shares memory with whatever else you're doing on the machine. And so you're kind of forced to do threads at some level. But if you do threads, if you just do raw threads, you just assume all you've got is sequential processes that are sharing memory, then doing it right gets extremely difficult. We went through, for example, this producer-consumer scenario where, not producer-consumer, the listener pattern, okay, where you have a data structure that's getting updated by one or more threads, and then you have a bunch of other threads that are being notified. There's a notification happening to some other software component, for example, to display data in the cockpit, or do some actuation somewhere or something like that. I showed you that some extremely subtle errors can arise because of this sort of intrinsic complexity that comes with threads, because of the fact that the actions in the threads can be arbitrarily interleaved. So the question is, okay, what should you do? I mean, one possible solution is just say, well, get over it. Threads are hard. You spend a lot of time puzzling over it until you finally convince yourself it's right, and then you ship it. But there's better ways to do it, right? One of the key better ways is to overlay on top of your programming exercise some higher order principles that may be implemented using threads, but then the thread programming problem becomes one of implementing simpler pieces of infrastructure. Okay? So we're going to look at one example of that today, which is synchronous reactive models, which are a concurrent programming model that it can be implemented, in fact, entirely without threads, and in fact is used in safety critical systems. It's used by Airbus for the design of the control software in all modern Airbus aircraft. And it's one of the few, it's in the case of Airbus, they use a programming language called SCADE, which is a derivative of a synchronous programming language called Lustre. It's a French word, Lustre, if you pronounce it in English. And it's the only high-level language other than C that has been approved for use in safety-critical code in aircraft. So you're not allowed to use C++, you're not allowed to use Java if you write safety-critical code for aircraft, you're not allowed to use Haskell, you're allowed to use SCADE or C. Those are the only options. And this isn't because C is a safe language. We know it isn't, right? I think it's the only reason that C is permitted is because if they didn't allow C, then there wouldn't really be any option at all, right? And SCADE is still kind of an idiosyncratic thing off in a corner somewhere. Airbus is, I think, an early adopter of a technology that is in some ways not very mature, but in other ways actually very mature, because what I'm going to show you today is that the principles behind it are very rigorous. It gives you a concurrency model that you can prove theorems about programs relatively easily, okay? And that is an extremely valuable property in safety critical systems, and it's extremely difficult to carry over that property into arbitrary multi-threaded programs. Okay, so just as a reminder, okay, we're gonna base this idea of synchronous reactive programming on the actor model, which we've already seen, where, if you remember, we had an actor model for state machines where we're explicit about the input ports and output ports of a state machine. And the idea is that the state machine, the environment in which this operates, specifies that the state machine should react at some point in time. At the point in time, that point in time is conceptually an instant, irrespective of implementation. This is the semantics. It's an instant, right? Of course, nothing happens instantaneously in implementations, but what you want to do is you want to have a mental model that is in some sense pure, that it's got to have some sort of perfection aspects to it. And then when you implement this thing, you want to be able to guarantee that it in fact behaves like the mental model, and where what you mean by behaving like it has to be carefully defined. Okay? So in particular, what you want this thing to behave like is that it reacts instantly to inputs, which means that it simultaneously, at the time of reaction, it looks at all of the values at the input ports. Some will be present, some will be absent, and it will take actions according to the values of the inputs, and those actions could include producing outputs and changing state. Okay? Now, because we model this, the model says this is an instantaneous reaction, the outputs are actually simultaneous with the inputs. They're viewed as occurring at the same point in time. And we're going to leverage that abstraction in synchronous reactive models. Now, of course, any implementation takes time to do this computation to produce the outputs. What you have to be able to do is guarantee that the implementation behaves as if it had happened instantaneously. Okay? So if you remember, actually, there's a model that I think has this character that is actually very intuitive and very easy to accept, which is a continuous time model. Right? We use this to model the physical side of cyber-physical systems, like the helicopter example. Right? So there we had an actor whose input was a continuous time function. So the input is a function that maps reals to reals. The output is a function that maps reals to reals. The system itself is a function that maps these functions into these functions. Okay? So, and moreover, we had ways of composing actors like this. So the controller for our helicopter, for example, would take a continuous time signal input, which was the error measurement, which is the extent to which the tail was swinging in relative to how much we wanted it to be swinging, okay? And the controller would just simply scale this continuous time function. The helicopter itself was given by a differential equation or integral equation that relates the inputs and the outputs. And the key thing I want to point out is that it relates the inputs and outputs instantaneously, okay? This controller relates the inputs and outputs instantaneously. The feedback system is instantaneous, okay? And this is the key thing that I want you to say, okay, yeah, obviously, I know about these kinds of systems. This works, okay? And then what we're going to do, however, is we're going to do this same kind of instantaneous feedback with software, and most of you are going to refuse to accept it, okay? Even if you can accept it in this case, you're going to refuse to accept it when it comes to software because it's going to be difficult to get your head around the abstraction, okay? And I'm going to try to help you do that today, all right? So the key point is try to accept the fact that, okay, notice one thing. There seems to be kind of a causality loop, right? What is the value of E? Well, the value of E is the difference between phi and whatever is on here at an instant. Well, what's on this feedback line? Well, what's on this feedback line is whatever the output of the helicopter is. Well, what's the output of the helicopter? Well, that's obviously going to be dependent on what the input to the helicopter is. Well, what's the input to the helicopter? Well, that depends on what the input to the controller is. Okay, there seems to be a causality loop that would lead you to not being able to draw a conclusion about this. But we can, right? And in fact, what breaks that causality loop is the fact that we're doing an integration inside of the helicopter model. Right? The integral equation here that relates the input and the output of the helicopter is what enables this feedback loop to actually have a well-defined meaning. Okay? So we're going to do something similar with software where we can build these kinds of feedback systems where the actors now are software modeled as state machines. The feedback is going to be instantaneous, and we're going to show that under certain circumstances it has a very well-defined meaning. Okay? So what we're going to do is take this same notion of composition that we're using here, which is synchronous simultaneous composition. So I want to point out that this is a concurrency model. Because if you think of the helicopter as a process, it is at least conceptually operating at the same time as the controller. Now again, in this case, that's easy to accept because it probably is physically operating at the same time as the controller. Okay? When we go to software, it may not be physically operating at the same time as the controller, but we're going to use a mental model that it's operating at the same time as the controller. And again, that's not anything new because in the case of threads, the mental model is that they're executing simultaneously. Physically, they're not usually. They're interleaving, okay? But the mental model we use is that they're executing simultaneously. Okay, so suppose we have two state machines, okay, which are shown in these white boxes. And actually, before I go to this, let me just switch over to the sketchpad here, and I want to point out a couple of things about this. In the case of a continuous time model, an actor with an input port and an output port has input functions that have the form of a mapping from the reals to the reals. Okay? In the case of a state machine, we can talk similarly about a structure for the input signals, right? But we can in fact have it be a mapping from the reals to some alphabet where the alphabet has to include some absent signal. Okay? So we allow for discrete signals here, and we can say, well, all right, that you know, the input has a value at all times. Most of the time it's absent, perhaps. Okay? But the right model to choose for the inputs here depends on what the semantics is of a reaction of the state machine. Okay? And let me remind you of three different semantics we've looked at. In the context of hybrid systems, the state machine was reacting all the time. So reactions were continuous and ongoing, even when those state transitions occurred discretely. We had other state machines that we looked at that were event triggered. So when an input became non-absent, a reaction would occur. Okay? There are other state machines that we looked at that were time driven. So they would react at specified points in time, whether inputs were present or not. Okay? Those are all legitimate models. Now, with the exception of the hybrid systems, all of those are amenable to an input model that is simply a mapping from natural numbers to the alphabet, including the possibility of absent. Okay? Where now x of n is the input, x of n is the input at the nth reaction. Okay? So the n in this case doesn't necessarily directly represent time. It's just whatever model we're using for reactions, on the nth reaction, x of n will be the input. Okay? So this is the model that we're going to use now for state machines. We're going to just talk about their reactions whenever they occur, and we don't really care for the purposes of this model whether these things are event triggered, time triggered, or something else. Okay? Okay, so there's a few key questions that we have to ask when we do composition. All right, so if I have one state machine, which has a set of states, a set of input valuations, a set of output valuations, an update function, and an initial state, which I might be able to represent all of these things using a bubble and arc diagram. Okay? This thing has its context determines when it reacts. Okay? If I compose it with another state machine, I can treat the two together as a state machine. But I have to define what a reaction of the composition is. Okay? Because now the composition itself is what gives these two state machines their context. So in the synchronous reactive model, a composition always means that the composed state machine, this one, its meaning is given by simultaneous and instantaneous reactions of the component machines. Okay? Oh joy, we get the garbage truck now making massive amounts of noise. So in the case of side-by-side composition like this, that's an easy thing to accept. In the case of feedback composition, it's going to be much harder to accept, and it's going to have some profound consequences. Okay? So side-by-side composition is relatively straightforward. Cascade composition is a little bit trickier than side-by-side. Okay? Because when we talk about these two state machines reacting simultaneously and instantaneously, but there's a little bit of a problem. How could they possibly react simultaneously if one of them is providing data to the other? Okay? We're going to look at the subtleties that can arise from an abstraction that is actually a very clean abstraction with a very clean mathematical foundation that says Yeah, they're reacting simultaneously and instantaneously, even though there's a causal relationship between their reactions. Okay, so let's look at a specific example of a cascade composition. So here's a very simple cascade of two-state machines. We have a pure input signal A, okay, and pure output A. So all the signals here are pure. They're either present or absent. When this thing reacts, A will be either present or absent. The initial state is S1. If A is present, we take a self loop and we make B present, okay? If A is absent, we take a transition to S2 and we make B absent. Okay, so in some sense this is a no-op, right? It just passes the input to the output, but it's the key is it is producing an output. At least it's a no-op in state S1. Okay? In state S2, regardless of what the input is, the output will be absent. Okay? Now this other state machine starts in initial state S3, and if B is present, it takes a self loop and produces output C. If B is absent, it transitions to S4, and the output will be absent. Okay? Now, if we want to define the meaning of this composition, one very clean way to do it would be to give an equivalent single state machine. Okay? So the idea of a composition is that the composition is a state machine that also reacts, and when it reacts, it will make a change of state and produce outputs. Okay? So what is that composition state machine? Okay? There's something very counterintuitive about this composition state machine. Okay? But let me just walk you through what the composition state machine looks like. It's got an initial state that says, okay, we're in S1 and S3. If A is present, I will take a self loop and produce the output C. If A is absent, I will go to S2, S4, okay? And the output will be absent. Okay? If I'm in state S2, S4, then under whatever the input is, the output will be absent. Okay? And if you reason through how this thing behaves for arbitrary inputs, given that, if you think of this thing reacting first to determine whether B is present or absent, and then this thing reacts to determine whether the output is present or absent, then the output will be as given by this state machine. Okay? Notice that these two states are not actually reachable from the initial state. So what this says is you can never be in the situation where your state is, you're in S2 here and S3 here. So let me give you a minute and see if you can identify why this is counterintuitive. What is counterintuitive about that? So to give you a hint, right? Why is it counterintuitive that this particular state, S2, S3, is not reachable? Yeah.
Intuitively, you would think that machine A reacts and that machine B.
Right.
You would expect A to go to S2 and B to remain S2.
Right. So intuitively, if you think of these things as sequential operations, you think, well, this machine has to react before this one because its output is going to determine how this one reacts. So it would seem that, gee, you do have to move to state S2, and upon moving to S2, all of a sudden in a transient situation, you will be in the state where you're in S2 here and S3 here. Okay? But that's not the way these machines work. That state, S2, S3, is not in fact reachable. That is the definition of the synchronous composition. It is not a reachable state. Yeah?
So when you introduced this, you introduced the
Right.
but the reason I intuitively understand the feedback system is because I know time enough to see the point where the inputs were different. So the reason this
Right.
right? And so my question is, how do we reconcile
Right. That's right. So let me give you an operational view. So I think, I mean, you've zeroed in on exactly why it's hard to accept these things, right? It is the discreteness of it, and the fact that any computer implementation is going to be discrete, and it would seem like it also needs to be sequential, right? It's got to do things in a step-by-step fashion. But there is a step-by-step fashion that has this semantics, okay? So let me explain what it is. So the step-by-step fashion is that we're in state S1 at the reaction. We determine what the output is, given the input, but we don't make the state transition. We just determine what the output is, okay? Once we've determined what the output is, we can determine what the output is from this guy. But again, we don't make the state transition. Only after we've determined all the outputs, then we simultaneously make all the state transitions. So there's an operational procedure that corresponds to the synchronous semantics. Okay? And the key thing is that when you implement these things, you have to actually ensure that whatever operational procedure you use to implement it behaves as if that were the case. So in particular, if your implementation does go through a transient state of being in S2 and S3, that has to be unobservable from the outside. Otherwise, your implementation is incorrect. If there's any way to observe that you were in this state, then your implementation is not correct. Okay? Which makes it a little tricky to implement these things, but because as I'll show you, these things have a definitive mathematical meaning, you can check correctness of implementations, okay, very systematically, which is the real value in this. So you've got a concurrent composition of two systems where you can check correctness of the implementation. Moreover, you can write down the meaning of the composition as a single state machine, which is a very understandable thing. This enables you to do verification on this. So for example, suppose that S2, S3 is an unsafe state, okay? Then a correct implementation of this system is safe. An incorrect implementation would not be, okay? So simultaneous and instantaneous is the thing that you have to be willing to accept. And when we go to feedback now, if you haven't accepted that yet, you're going to have a hell of a time with feedback. Okay? So feedback looks like this. Okay? Now, it turns out that every composition, every actor composition can be viewed as a feedback composition. So if you think, well, okay, maybe I'll just avoid feedback, then it's not going to work, right? Because in fact, the fact is that anything you do can be viewed as a feedback system, and therefore your model has to give some meaning to feedback systems. Okay, so let me show you how that is. Well, this is, of course, naturally a feedback composition, but let's look at an arbitrary composition here. So here I have F1, F3, F2, and there is feedback. I mean, you can see a cycle here, okay? But the way that we're going to look at an arbitrary composition like this is we're just going to take all of the actors and stack them up, okay? And then draw a yellow box around them, and then run the wires in a feedback path. So then we can abstract that yellow box as something that has input ports and output ports with feedback paths. Okay? We can take these feedback paths and aggregate them into a tuple of feedback paths. And this function is a rather simple thing. It's a side-by-side composition. Side-by-side composition was the easiest one to understand. Okay? So if we understand feedback composition, we will understand cascade composition, as well as feedback, as well as side-by-side, because all three of those styles of composition are present in this example. Okay? So let's do another little exercise here. If I have two actors, A and B, how is that a feedback system? You can't see what I'm doing. There we go. I have two actors, A and B. How is that a feedback composition? Yeah, Raphael.
Stack them.
Stack them.
A goes in with B.
A, B, draw a yellow box. Abstract the box. Feedback. Whoops. Okay? Everything is a feedback system in actor composition, so we might as well just bite the bullet and understand feedback, and then we'll understand everything else. Okay? Okay, so the key with feedback is actually the same as the key with the continuous time system that we saw. So in particular, here we've got a feedback system, and this wire that goes from here back to an input, okay, what is the meaning of that wire? Well, the meaning of the wire is that the signal here and the signal here are the same, right? That's what we mean by a wire in one of these diagrams. Same thing here. What we mean by this wire is that the signal here and the signal here are the same. So if I have an n tuple of signals, that just means these are the same signals. Okay? So if I accept that, then this function, the behavior of this system is what's called a fixed point of this function. Okay? If F1, F2, and F3 are state machines, then each one implements a function from inputs to outputs, if they're deterministic state machines, right? So a side-by-side composition of such functions also implements a function. So the behavior of the system is simply a function, is a fixed point of that function. A fixed point simply means that it's a value of s such that f of s equals s. Okay? So the mathematical meaning of these synchronous reactive compositions is the fixed point of these functions. Okay? Now, the interesting question is, well, is the fixed point unique? And does it exist? Right? If it's not unique, then maybe the system isn't determinate, or maybe it's otherwise flawed. Okay? If there's no fixed point, then it's kind of obviously flawed, right? Because that means the feedback composition doesn't actually have any meaning. Okay? So fixed point semantics says you consider an interconnection of actors, you reorganize them into a stack of actors, you abstract them into a single function, you abstract the signals to aggregate them, and you look for a fixed point. Okay? Now, we would like this fixed point to exist and be unique, and we would like to find a constructive procedure to find it. Okay? What I mean by a constructive procedure intuitively is simply something I can implement in sequential software. Okay? I'll show you that actually there are feedback systems for which there is no constructive procedure for finding its behavior. So it turns out we probably, in order to implement these things in sequential software, we have to reject a class of systems. Okay? Okay. This is a little bit of an aside. But okay, let me go ahead and do this aside, and then we'll take a 3-minute break. Okay. The input and the output here, the meaning of the wire is that it's the same signal. Okay. In order for it to be the same signal, of course, it's got to take on the same values. In fact, in general, with any connection, we're going to have a constraint that the data types at the output port that are connected to an input port have to be compatible. They don't necessarily have to be identical, right? The data that can be produced at the output needs to be a subset of the data that can be accepted at the input. Okay? That's a type system constraint. But, okay. The key thing is that we have to check for that, of course, in any composition. But having checked for that, we can then define this function f, and f has the following form, if we're restricting our domain of discourse to state machines. Its input is a function, and its output is a that maps the natural numbers into whatever valuations are provided, the alphabet, with the inclusion of possible absent, and the output has a similar form. Okay? And so our type constraint is simply that the alphabet at the output has to be a subset of the alphabet at the input for state machines. Okay? So we're looking for a fixed point of a function whose domain is a set of functions and whose range is a set of functions. That's not very easy to find in general. In fact, basically, the field of differential equations is all about finding such fixed points, and it's a huge topic that works for a rather narrow class of systems. You have to have certain continuity constraints, and you can find closed form solutions for only certain kinds of differential equations, and those closed form solutions are fixed points of this form. In the context of state machines, however, our lives are much easier than with differential equations. And the reason is because state machines have a very simple behavior that can be described sequentially, and we can isolate the behavior at each reaction. That's the key. Okay? So why don't we take a 3-minute stretch break, and then we'll look at how to reduce this problem to finding fixed points at each reaction rather than over all possible reactions. And that will leverage the formalism of state machines. Okay, let's go ahead and resume if we could. So, does anybody have any questions or comments about what we've done so far? It's okay, don't worry. Any questions or comments about what we've done so far? Okay, so the question is, why does a fixed point have to be unique? Well, it doesn't really. I mean, the question is, what do we mean by a system that has more than one fixed point? Right? One possible interpretation is that the system is non-deterministic. And then the question becomes, well, if you're going to implement it, how would you implement it? Right? And I think, it's a legitimate question, and you could allow systems that have non-unique fixed points, but you have to answer that question about what you mean by that and how an implementation should choose among the possible behaviors, right? Yeah, life is a lot simpler if it's unique, is the bottom line, and so we're gonna strive for unique fixed points, and in fact, I'll show you conditions under which they're essentially guaranteed to be unique. Okay. All right. So the key idea here is that a state machine, its input is a sequence of input valuations, right? But at each reaction, the state machine itself defines an input-output function. Okay. It's just that the function changes over time. It depends on the state of the state machine. Okay? So we can, for state machines in particular, we can define a firing function which simply says at the nth reaction, there is a function that maps inputs to outputs. These are the input values, not the sequence of values. Okay? It'll be dependent on what state the state machine is in. Consequently, the function itself changes in each reaction. Right? So the entire sequence of outputs in this case, which is this fixed point, okay, is a function of n, which is the index of the reaction. And at each reaction, we in fact are looking for a fixed point again. But now it's a fixed point of this firing function, which is has a much simpler structure. Okay, the firing function doesn't have any it's not a set of functions, it's just a set of values. Okay? So we can now break the problem into two pieces, right? The first piece, this is the operational description that I was giving to Ryan earlier. The first piece is simply to figure out what this function is at a given state and then evaluate it to determine what the outputs are given the inputs. The second stage is to then figure out what the new function is for the next state. Okay, so we can augment the function after we've determined what the outputs are. And that's the operational procedure that gives you a correct behavior. So now the way to deal with feedback becomes simply determining the fixed point at each reaction given that you know what state you're in. Okay? So we define what we call well-formed feedback. And well-formed says that the solution at each reachable state, so for every reachable state, there's a function f of n, okay? And at each reachable state, the solution, there is a fixed point solution and the solution is unique, okay? So if either of these two problems arises, either there is no solution or the solution is not unique, we're going to call it ill-formed. Now, as I said before, you might be willing to accept non-unique fixed points, but for our purposes, we're going to reject them for the moment, and that keeps things a lot simpler. So we'll declare the model to be ill-formed if the solution is not unique. So here's an example of a well-formed feedback system. Okay, the initial state is S1. If the input is present, the output will be absent. Well, that's interesting because can this transition ever be taken? can't, right? What's the meaning of a wire? The signal here and the signal here are the same. So in order to take this transition, we would have to say, well, if the signal is present, it must be absent. If it's absent, it must be present. So, that doesn't work. Okay, so this transition is not ever going to be taken, in fact. Now, that doesn't mean there's something wrong with this state machine, because remember that what made this transition impossible to take was the composition. The fact that I wired the output back to the input. This is sort of a trivial form of composition because it's kind of a composition with itself, right? But the fact is I put a perfectly good state machine, put it into a context. That new context is defined by a state machine, okay? And in that new state machine, that transition can never be taken. Yeah?
Why not? If you're in a tube, you're going back to a spot. Is absent, so we're going to have another way.
But that would be in a different reaction, right? A reaction is instantaneous, right? At a reaction, because of the feedback loop, the output equals the input at that reaction, okay? A reaction, it would have to be a single reaction that took this transition. In that single reaction, the input has to be present to be able to take that transition. But if you take that transition, the output is absent in that same reaction. And it can't be both present and absent in the same reaction. Right? This issue of simultaneous and instantaneous is the thing that you have to accept to understand the semantics of this model. Okay? Okay, so what is the meaning of this system? Well, okay, so this transition can't be taken. What about this one? Well, maybe, but we don't know whether the output is absent. Whether the input is absent, which means, of course, we don't know whether the output is absent. So how do we know whether this can be taken? Okay? So how do we know? We're in state S1. How do you determine what the behavior of this system is? Yeah, Raphael.
Do you have to mandate an initial condition?
Well, we have an initial condition, right, which is that we're in state S1. Oh, on the feedback loop? No. There's no, the issue here is that, at a reaction, the input has a value and the output has a value. And the issue is that we don't know what that value is. And in this particular case, we can't know what the output is until we know, what the input is until we know what the output is, because the input is defined by the output. Right? So we can't say that the signal here is initialized to something and then, because what would that mean? It would mean that in a reaction it would be initialized to something and then change its value, but at a reaction it can only have one value. Right? So you can't change its value. Apurva. That's the key question. How do you decide on the output if you don't know what the input is? Yeah.
So if we assume there is an output, what happens to that?
Okay, so I think the principle behind the intuition that you just expressed, which I think is valid, is that we can look at this system and we can try all the possible outputs and inputs. All right, how many? In this case, the number of possibilities is limited, right? In a reaction that we're in state S1, there's only two possibilities. Either the input is present or it's absent. If it's present, then we know it must be absent, so that's a contradiction, so it can't be present. So it must be absent. That's the only other possibility, right? So if it's absent, then we know we can take this transition, and sure enough, it'll be absent. So that is at least consistent. That was the only possibility, therefore the fixed point was unique in this state. Okay? It was the only possible assignment of values to the input and output from among all the possible values. Okay, what about this state? Sorry? Right. So we can go through the same exercise and try all the possibilities and say, well, if the output is absent, then we would take this transition, which would make the output present. So that's a contradiction. So that transition can't be taken either. So the output must be present, which means the input is present, which is consistent and the only possibility. Therefore, the fixed point is unique, again, in this state. So in both states, and both states are reachable in this case, and in both states, the fixed point is unique. Raphael?
So doesn't trying the
It does, but in order for this procedure to work, you have to try all the possibilities. It's not enough to try one until you find one that works, right? Because we're interested in whether the thing is well formed, which means we need to know whether it's unique. Okay?
find one that works.
It's not enough to draw the conclusion that that is the behavior of the system. You could find more than one. Whoops. So you have to try them all to use this procedure. Yeah. Sorry.
Essentially, you're finding like one output per state, right?
In this case, yes. Basically, one way to think about it is that in each state, this machine defines an input-output function, right? So we have to look at each state independently. We only have to look at reachable states because we don't care how the system behaves in unreachable states. But for each state, we have to be able to find a fixed point.
So is that the same as a Moore machine?
No, because, although actually this particular example is the same as a Moore machine. This particular example has a rather simple property, which is that in either state, the output is determined because you can look at all the possible transitions out of this state, and they all produce the same output. But you have to be careful applying that, right? Because you have to be sure that you're not forgetting about an implicit stuttering transition. Whenever you use the reasoning that all transitions from a state exhibit a certain behavior, produce a certain output, you have to be sure that you're really looking at all the possible transitions, including the implicit stuttering transition. But in this case, we're safe because all the transitions are explicit in this model because we state what the behavior is, whether the input is present or absent. So there's no implicit stuttering transitions here. So in this state, all of the transitions out of the state produce absent, therefore the output has to be absent. And in this state, all the possible transitions produce present, so the output is present. So this particular state machine has state-determined output, which is the character of a Moore machine. Okay? So if you have a Moore machine in a feedback loop, then you can simplify the evaluation procedure. You no longer have to consider all the possible inputs and outputs. Okay? You can instead just look at what the outputs have to be given the state that you're in. Right? So you want to take advantage of that simplification, especially if your input alphabet is infinite, which it often is, in which case you can't do the exhaustive search. Dorsa, you had a question?
So here in this case, whenever we have feedback, so they have.
Right. Yeah.
Did we need to have those like self-transitions?
We could get rid of those. In fact, but I mean, I want to emphasize that there is a difference between this state machine A and the state machine defined by the composition that includes the feedback connection. Right? So the goal of this is to be able to build up systems from pieces that are operating concurrently. In this case, this is a trivial example, so there's no concurrency, but you will see that you can generalize this idea, right? So, A might be defined, designed by somebody else. You bought A, and then you put it in the feedback loop. And how does it behave? Well, you can't just change A, right? But you can use this, you can give a meaning to this system. So in particular, this composition with the feedback connection is defined by this state machine. Okay? This state machine gives the semantics of this composition. The same way we did this same trick for the cascade composition. Where was it? Here. Right? We defined the synchronous cascade composition of these two things to be given by this state machine. Okay? That's a way to give semantics to a concurrent composition, is you give it a non-concurrent equivalent system. Okay? So we do the same thing here, where the equivalent state machine it looks very similar, except that it doesn't have the feedback loops, but notice that it also doesn't have the input anymore. Why doesn't it have the input? Because this composition doesn't have any inputs. Right? Notice that. Okay? That's it's easy to forget, right? But this composition, because the feedback wire is part of the composition, there's no inputs. There's no externally provided data. There's observable data, perhaps, right? Output B. So as a consequence, the equivalent state machine can't be dependent on inputs, and in fact, it isn't, right? The way this state machine behaves is just in every reaction, it alternates between state S1 and S2, and B alternates between present and absent. Okay? So that's a well-formed feedback. Now let's look at an example of an ill-formed feedback. And this is one where there is no solution. Yeah, Apurva.
If you have multiple fixed points, would that make your machine non-terminate?
Well, we will define it to be ill-formed, okay, which means that we're just going to reject it. Now, you could alternatively accept it and interpret it as a non-deterministic machine, okay, but then you have to provide some implementation that somehow resolves that non-determinism, right? But we define it to be ill-formed if it has more than one fixed point. So here's a slight variant of this system where there is no fixed point when we're in state S2. Okay? In state S1, everything's the same as before. The output will be absent, the input will be absent. In state S2, however, if the input is absent, the output will be present, and if the input is present, the output will be absent. And therefore, although there's nothing wrong with state machine B, there is something wrong with the feedback composition. Okay, it's self-contradictory. So we declare that to be an ill-formed composition. So this is an example that has the behavior that Apurva was concerned about. In state S1, if the input is present, the output is present. If the input is absent, the output is absent. Okay? So there are two possible behaviors in state S1 for the composition, even though, notice, state machine C is determinate. So, but the composition is non-determinate. This is one of the reasons that we are strongly biased towards rejecting ill-formed compositions, is because it's very disturbing if you take a bunch of determinate components and compose them and get a non-determinate system, right? So if we reject these systems, we can avoid a lot of problems, right? We have to be able to systematically reject them. Now, there's a problem. So in general, if you have a state machine, you can always use this to determine whether it's ill-formed or not. Start in the initial state and consider all the possible inputs, determine what all the corresponding possible outputs are, and see if they're consistent. And if there's more than one that's consistent, you reject it because there's more than one. If there are none that are consistent, you reject it because there aren't any. In both cases, it's ill-formed. But in practice, your data types are usually big enough and possibly infinite that you don't really want to be doing a search over all possible inputs. That's not a very practical thing to do. So what we'd like to do is provide a constructive procedure for finding the fixed point. Now, I should tell you that in the research in synchronous languages, which started about 25 years ago, so it was started by people in France. Okay, it was a very French thing for a while. Okay, and it's kind of broadened beyond France these days, but it very much initiated there. It initiated with a family of 3 competing programming languages: Lustre, Signal, and Estrel. And Estrel is in some sense the closest to these concurrent compositions of state machines that we're looking at, because it had a state machine semantics. Okay, the other ones were more like a synchronous version of LabVIEW, where the components were input-output functions without an explicit description of their state machine behavior. In Estrel was the language that it turned out, because it was using state machines, it was in some sense significantly richer than Lustre, but not as rich as Signal. Signal, it turned out, was capable of expressing non-determinate systems and highly asynchronous systems. And consequently, its analysis turned out to be really much more difficult. But Estrel would sort of hit a sweet spot of being very expressive and rather hard to analyze. Okay? And it took years before the originators of Estrel, who were primarily, I guess, Gerard Berry is the main guy who was kind of the brains behind it, to realize that he had to actually restrict the space of state machines that were allowed. Initially, the first version of the first 4 versions of the Estrel compiler all would fail to compile some perfectly valid Estrel programs. And on the 5th version, Gerard simply decided that we have to be able to reject some programs. Okay? And he invented this concept of what he called a constructive semantics. And what this constructive semantics does is it defines the family of programs that can be compiled. Okay? And that's ended up what people actually use in practice for synchronous semantics. So the way constructive semantics works is you simply start, it's sort of intuitively it follows what you wanted to do, which is you initialize the value of all the signals, but you don't initialize them to something in their alphabet. Okay? Instead, you initialize them to a special symbol that means unknown. I don't know what it is. Okay? And then you determine as much as you can about the outputs. So given the input, you figure out what you can determine about the output. And if you can make some of your signals known, then you make them known. Okay? If they all remain unknown, you've already found a fixed point in a sense, but the fixed point is that everything is unknown. Okay? So I want to give you a little sketch of how this works. Whoops. So, oops, did I lose the connection? No, I lost the connection. ECS not work. Okay. If our signal alphabet is, if we have a pure signal like our signal A, it can be either present or absent. Okay? We augment this space with one other possibility, which is unknown. Okay? And we augment the domain of the function f then so that it maps the set present, absent, and unknown into present, absent, and unknown. Okay? And in addition, we can show that under certain very mild constraints, under certain very mild assumptions, this function can be assured of always being monotonic in the sense that unknown is less than present and less than absent. Okay? So what this means is that if you have a feedback system with several signals being fed back, okay, and you have a function f of n, the inputs all start unknown. Okay? If one of them becomes known, so this becomes present, for example, upon an evaluation of this augmented function, okay? So maybe you evaluate this augmented function with all inputs unknown. This becomes present, and these two remain unknown. You can now change this to present, unknown, unknown, reevaluate the function, okay? And maybe this becomes absent, okay? You can now change this to absent, reevaluate the function, and maybe this becomes present, okay? You can now change this to present, reevaluate the function, and if you find that you get present, absent, present, then you've found a fixed point. But how do you know that the fixed point is unique, right? Well, the key is that when you do these reevaluations, so that when you're at the state present, unknown, unknown, for example, okay, when we reevaluate this function, we don't allow the function to change its mind and make this absent. If it previously decided it was present, it's present. And it will remain present no matter what you do to the signals. Okay? If you look at it from this perspective, you only ever move up in this hierarchy. A signal can move from unknown to present or unknown to absent. But while you're doing this evaluation, it can never move from present to absent or absent to present. And it can never move from absent to unknown. So you're always moving up, okay? And it turns out that monotonic functions, functions that have this character of always moving up in an order, have a unique least fixed point. So there's a fixed point that you will always find that is the lowest one in this structure, okay? And that unique least fixed point gives the semantics of the model. Yes, Raphael?
Do you just define it to not be allowed to change it, or where does the restriction come from? So you said because once you determine.
So it turns out that these, for the state machines that we've defined, the functions f of n are always monotonic. In this sense, just because they're state machines. Okay, as a consequence, let me show you how this works. Okay, so let's go through this example. So here is let's go through an example that is constructive. This one, okay? We start with the feedback signal unknown, okay? At that point, we augment this function, okay? So now, instead of just the function that corresponds to being in state S1 tells us not only what the output is if the input is present or absent, but it also has to tell us what the output is if the input is unknown. And in this case, it actually can tell us that the output is absent if the input is unknown, right? So because all of the possible transitions out of state S1 produce absent, okay? As a consequence, the function, the augmented function, given an unknown input, can produce an absent output. Yeah.
Well, if one of those paths had beyond it, then your output would be unknown.
That's right. So if one of these paths had a signal, so if we look at the ill-formed example, this one, in state S2, right, what is the function? The augmented function. Well, if the input is unknown, the output remains unknown. The augmented function has a fixed point, unknown. That is a fixed point, and it happens to be, it is in fact the lowest fixed point. If there might be other fixed points, okay, But this procedure of starting with unknown and evaluating these functions works its way up this structure. The structure gets more complex as you have more signals and more values, right? But it works its way up its structure until it finds a fixed point. It's guaranteed to find a fixed point, and the fixed point it finds will always be the unique lowest fixed point in this structure, and it's always unique, okay? So in this case, the unique fixed point for the function that when you're in state S2 is unknown. Therefore, we declare that to be the behavior of the system. Okay? Now, I want to show you that this does reject state machines that we wouldn't have otherwise rejected. Okay? So here is a non-constructive, well-formed state machine. So here, the input values can be 0, 1, or absent, and the output values can be 0, 1, or absent. Okay? When we're in state S1, if the input is 0, the output will be 1. So that's kind of bogus. We're not going to be taking that transition, right? So the input can't be either 0 or, well, it can't be 0, right? If the input is 1, what's the output going to be if we're in state S1? That's a stuttering reaction, so the output will be absent. So if the input is 1, the output will be absent. This is what why you have to watch out. I'm using now the exhaustive search procedure. I'm looking at all possible inputs. Okay? If the input is 0, the output is 1, so we reject that. If the input is 1, the output is absent, so that's okay. That's rejected also. So the only remaining possibility is that the input is absent. Therefore, I have a unique fixed point, which is that the input is absent. But the constructive procedure can't find that, right? If the input is unknown, the augmented function tells us what is the output? It's unknown. I don't know whether the input is 0 or absent. So I can't tell you what the output is. So this state machine gets rejected by a constructive semantics, even though it has a unique fixed point. Yeah. Sorry? So in this notation, we implicitly always include the possibility of absent. Right. It does work out. This machine is well formed. In state S1, it has a unique fixed point. The constructive process doesn't find it because the augmented function is a property of this state machine, not of its composition. It doesn't know. The augmented function has no idea how this thing is connected. Okay, it's a property of the state machine. If all you know about the input is that it's unknown, what can you tell me about the output if you're in this state? It's still unknown, right? So the constructive procedure rejects this composition even though it has a unique fixed point. This was the breakthrough between version 4 and version 5 of the Esterel compiler. And the way that this came about, this came about over the course of about a dozen years, where people kept finding counterexamples that would break the compiler. And they were real puzzlers, these counterexamples. Okay, and they had this non-constructive behavior. And the versions 1 through 4 of the compiler were trying to basically implement the exhaustive search procedure. And Gerard Barry finally said, that's not going to work. I can't make a compiler that does exhaustive search in general. And so he redefined the language to reject non-constructive programs. Okay? So part of the trick in this, of course, is to be able to figure out what that augmented function is, right? And the way that is done in practice is using what people call this must-may analysis, which means given whatever you know about the input, what must the output do? Okay? So in this case, for example, if you're in state S1, all the transitions out of this make the output absent, therefore the output must be absent here, no matter what the input is. Okay? So you can systematize this must-may analysis and turn it into a compiler. All right. So if you have multiple signals, you follow the same procedure. You start with everything unknown. You repeatedly evaluate the function. If you have multiple functions, you use the same procedure. You start with everything unknown, and you evaluate these functions, interestingly, in arbitrary order. Doesn't matter what order you evaluate the individual functions. Okay? You will eventually converge to a unique least fixed point, which will give the meaning of the composition. So this generalizes to arbitrary scales. Okay? You can have any number of compositions. You only have to know what the functions are for the individual actors to do this. So it scales very nicely. Right? Procedure is just start with everything unknown and evaluate functions in any order. Okay? So intuitively, you could say, well, in this, I should evaluate function f3 before f2. The constructive procedure says, doesn't matter. You can evaluate f2 before you evaluate f3. Okay? Any order will give you the same answer. You just keep evaluating them until you hit a fixed point, and the fixed point is guaranteed to be unique. All right, I want to emphasize, how does this compare with threads? If you implement this, how would you implement this? Well, you're given a program which is, you're given a bunch of state machines and their interconnections. You write a compiler. The compiler effectively gives you a new state machine for the whole program. Do you need interrupts? Actually, you don't need interrupts. You don't need context switches. Okay? The implementation of this is a single thread of control with no threads in it at all. No shared memory no arbitrary interleaving, perfectly deterministic program. This is why they like it for safety critical systems. Now, of course, that has limitations. If you're doing I/O, right? Suppose that F3 is providing sensor data, then the implication is that you can read that sensor data only when the whole thing reacts. So effectively, you're polling your inputs. You can't be event triggered. You could make the whole system event triggered. So the whole system reacts when an input occurs. Okay? But you're not going to have the situation where an external event occurs and part of your system reacts. That's not allowed by this model. Your whole system has to react together. Yeah?
So does this mean that this whole conclusion of this entire thing is that
You effectively serialize it, but I want to point out that you do that with threads too. Right? And if you're running on a single CPU, the implementation is always one instruction after another. The problem with threads is that you have no idea what the ordering of these instructions is. Whereas in this model, the behavior is completely determined by the model. Okay? So it's kind of at the opposite extreme of threads. It's very deterministic, even though it's concurrent, because you can build up big systems where conceptually all of these things are going on at once. Okay? The implementation gets serialized, but it does in threads too, but it gets serialized in a way that is well-defined and deterministic. So that's why they like it for these kinds of safety critical systems. It's a very powerful property. We're going to look at some models that are sort of looser than this. In particular, data flow models allow for more asynchrony, but still have some very nice concurrency properties that are absent in threads. So we'll look at those after a couple of weeks. Okay. Have a good spring break. Work on your projects. Even if you're away, think about your projects.